I typically start with the Ericsson Research overview. I guess you know Ericsson Research since you have worked with Hugo for a couple of years, but maybe what I want to say here that we are located down in southern part of Sweden in Lund. So if we would have been in Kista today, we would have said, it's kind of so there's a struggle between the southern part of Sweden and in Stockholm. But anyway, we located down in Lund, me and Pat, and I think Hugo was actually studying down here with us.
I grew up in outside of Lund, so I lived there for 25 years, and I did my undergrads and masters at the Lund University.
So that's the place to be. So today it will be me, Johan, and with me I have my colleague Per Persson, and we've been working together since 2004. So that's 16 years we go back. And well, Per will take care of the lab, and I will do the talking today. So this is kind of a high buzzword density lecture. So please ask. I typically use lots of words that I try to explain them, but sometimes I'm just too stuck in my own bubble to realize that things are not self-explanatory. So please feel free to just ping me and say, what does that actually mean? And chances are that I don't know. Sometimes we just go along and use terminology that it's just we're getting used to that. So please feel free to just tell me when it's not clear. Anybody knows where this quote comes from? What I cannot create, I do not understand. Any takers? And not Hugo. I guess not. So Richard Feynman, the famous physicist, when he passed away, was on his blackboard. He said on the top left corner, he said, "What I cannot create, I do not understand." And I think that is a nice sort of motto for working with cloud. That on one hand, the concepts that we talk about are very, very simple. Start a virtual machine, connect those together, do work, but in practice, it's actually quite difficult. And we try to make this as hands-on as possible in order to be able to teach you something. So this course is this 2-day course is 2 hours of talk, and then it's 10 hours of you guys sweating away on things, and then we have 1 hour of talk. And I hope you will learn a lot through those 2 days. And the setup today is we go through a little bit. We will learn what is a cloud, what does a cloud application look like, so what is special about them. We will tomorrow reflect on some of the fundamental limitations on distributed systems, what you can do and what you cannot do. Can you reason about them? We'll talk a little bit about failures. When you do cloud computing, it's large scale and things will always fail. So how can you work with that? And then we'll also finish off with, what is next? Where are we heading now? And now at that point, you will know what cloud is. So we will move on and see which is the direction that cloud is going today. So here's sort of the learning goals. Maybe we should not read everything that says here, but there are 2 lectures. This is a 2-hour into the cloud. And we're going to run it by 2 times 45 minutes, so you get a break, don't worry. And then we have cloud trends and a note on distributed systems tomorrow. And then you have an assignment today. You're going to make a cloud application by hand. And then you're going to find out a way to automate it. And you should already have accounts on the Ericsson Research Data Center, which it's a cloud called Xerxes. I don't remember what Xerxes stands for. I think it's External Ericsson Research Cloud Environment something. I don't know. But that's what we use for our external interactions. And that's so if anybody do not have a working account, you should ping me and Hugo right this moment, I think. And the prerequisite for this course, as we said, is some Python know-how. You don't need to be Python experts, but it's good to know your way around Python. I don't think you will be programming much Python actually, but it's always you will be some Python, and it's good to know some basic operating system skills. It will involve some basic Linux stuff, and access to a computer where you should already have installed Docker. And again, if you have not installed Docker, maybe you should ping Hugo and Pad and do that in the background, because I think you actually will need that when you do your homework. So do we have anybody who has not have an account and installed Docker? Oh, yes.
I know one that had a problem with the password, but I pinged Rodrigo to ask to have them resent, and there had been a little bit of an issue of distributing the program files because it's executable.
Yeah. Okay.
But, I'm working on it in the background.
Cool. Thanks.
Yeah, I also have an issue with Docker. I am on Windows. I cannot find the file sharing tab under resources. I don't know if there is an easy fix for that, or I installed the wrong version of Docker, or I should use Linux straight off.
I haven't used Windows for 10 years, but I know that Hugo is using Windows. So maybe you guys can try that on a. I think there is a team support channel also that Hugo is running.
I have found it.
Okay. So can we chat a bit? Okay. Thank you anyway. I'll let you go and we chat.
Yeah.
Thank you.
Okay.
I appreciate. I mean, come on, it's good that I hear your voices. I like that. Okay. So the fourth component, the fourth prerequisite here is a lot of patience, because you will experience hiccups in it's large scale network, so you can try the same command twice, and the second time it works better than the first time, since the delay were less or something. But working with real systems will provide you with real problems. Okay, so patience is a good thing to have. So before this session, I sent out a paper. This is an old paper from 2010, I think. It's from the Berkeley crowd. Those Berkeley people are probably the world leading when it comes to all things cloud. Persons like Stoika and Scott Schenker and others. So this is a fairly good paper, and it gives you idea of the foundation for cloud and how it all started. They actually published an updated version. It's called the Berkeley View of Serverless Computing, and we will touch upon that later. But it is worthwhile read, and I will send out the other paper for you. I don't expect you to read it tonight, but if you're interested in cloud and where we're going, that's also a good read. Okay, so this is the home turf for me and Pat. This is the Ericsson Research Data Center. I'm just it's nothing big. It's 340 square meters. We have roughly 1,000 plus servers, and that makes it half full. I think we can host up to 3,000 servers or something like that, depending on the mix of GPUs and servers. And on this, we run 2 cloud installments, one external and one internal at Ericsson. It's a fully redundant facility. So on the down right, you see to the left in the picture, the round thingy here, it's a diesel tank, and then it comes the power generators that is in case of outage in the power, and then you have the cooling to the right, and that's where we play around and build cloud systems for different research purposes. So we do both provide research cloud for people to use, but also experimental cloud installations for experiments on how you design and build and operate cloud. And we are sort of in the borderline between early commercial to very innovative stuff. So this is the example of the more commercial-like things we do. So for example, SEB, which is a big bank in Sweden, are running some remote advisory things here. We have Nordic Wave was a project where cars and trucks in the Nordic countries were connected to the cloud, and then they reported back, if there was a bump in the road or an ice patch or similar, and then that was distributed out to the other cars. And we're doing drone management with Telia, who is a major Swedish operator. We do micro weather was a application where you were sensing the quality of the microwave link, and then you could actually defer if it was raining, and then you could sell that data to as a service to the Weather Channel or something. So this is stuff we do, but that's not the focus. The focus is how to run a cloud, and running a cloud is very eventful. So not too long ago, or some years ago, but when we just started here, we had some outage that was due to a rat that chew off the fiber. So everything breaks when you do cloud. So everything has to be redundant. And so we will talk a little bit how you design your applications. And not only you need to design your applications for the servers and hardware to fail, but you need to design your hardware to be providing redundant channels for communication, for computation, for storage, for everything. So what is cloud then? Where does it come from? If you go to Google search and you look at when the term cloud computing start, you'll see that before 2008 it was barely nothing, and then the interest rose during 2009, 2010, 11, and what happened was in 2006, AWS did introduce a service called Elastic Compute Cloud. And about that time, Amazon did have lots of spare capacity because they wanted to be able to serve the customers on events like Black Friday and other days, Labor Day, when people are shopping a lot, but the rest of the year they actually did not need that capacity. So if you have spare capacity, there's one way you can sell that, and one way to selling that was to sell virtual machines and virtual networks. So they started to provide that as a service in 2006, and rapidly they added more and more services to their platform, and eventually they had a very full-fledged cloud platform. And that's sort of the driver for this whole evolution of cloud. And just to understand how big cloud has become, already in 2014, cloud computing was the 6th largest consumer of electricity. And we should remember in 2000, those numbers are not published anymore, maybe for good reasons, but we can be absolutely certain that cloud computing has grown by several factors since this Greenpeace. So the Greenpeace is every year publishing a report called Clicking Clean, but it's the last one I found was 2014. So this is a rather worrying number, I would say. So what is cloud computing? There are many different definitions of this. I will just mention that it's maybe it's just a buzzword. It's clearly not a scientific topic, at least. So Richard Stallman says worse than stupidity, it's marketing hype. Somebody is saying that is inevitable, and whenever you hear that, it's likely to be a set of business campaigning to make it true. And I think that's actually some truth to that. I think that cloud computing is more of a business model than a scientific topic. But we'll try to make it into something more scientific today. We'll discuss some definitions that are stricter than this, and we will try to figure out how it differs for the different types of cloud computing that does exist. So already in 1961, John McCarthy, who was one of the leaders of AI, he said that if computers of the kind I have advocated become the computers of the future, then computing may someday be organized as a public utility, just as a telephone system is a public utility. The compute utility should become the basis of a new and important industry. So if you think of this, how do we consume electricity, and how do we consume telecom and water and waste? And typically, the way you do that is not that you pre-order, you get an agreement with your electricity provider or power company, and then you plug in your lamp. And if you need more light in your house, you plug in another lamp, and so on. And so the idea is to think of when you use a cloud system, it works in the same way. If you need more compute capacity, you simply just use more capacity. And in the same way with electricity, when you consume electricity, you pay per watt hour, and not for and you don't need to pre-order the amount of what you're going to consume for the next 24 hours. And the same goes for water and waste. Telephone is slightly different, but the more you call, the more it costs. So in that sense, cloud computing is sometimes referred to as utility computing. Does this sort of analogy vibe to you guys? And do you think it's fair, or do you think it's not really okay? I guess you just think it's nice. So I like to think of cloud as sort of the illusion of infinite compute power and storage at your fingertips. So, and it's like when you get cloud, you're not limited to one server or one system or something that you actually have on desk. You can scale up to possibly, or at the illusion of infinite compute power and very large storage if you just have the budget to back it up. And I think that idea is will then have some effects down the line, because if you can think this big, what can you then create? And I think that is one of the things that makes cloud so fascinating. The stuff you can create when you think of this as your infinitely large computer. But the problem that we started to address with cloud was the following. The workload varies much, and that was sort of in the beginning with Amazon. They had to buy hardware to provision for the worst case, and that's of course a very common scenario. You have to make sure that you have to make a trade-off between not serving customers or buying too much hardware. And depending on your margins, when you run your shop or whatever service you have, that equation may look different. So if you look on the lower slides and lower pictures, which is taken from the paper that was sent out, and they say that the dark green here shows the unnecessary capacity, or the capacity that is not matching. So in the first case here, you're provisioning for peak loads, and the peak loads varies in this case as almost a sinusoid. And then the dark green is where you have overcapacity and your servers are not running, so you lose there. On the other hand, if you do some under provisioning, as a picture B, that will mean that regularly over the day you will not be able to serve customers. And depending on what you sell or what kind of service you have, if you're a Spotify, etc., that can be very, very expensive. So, and just to, sorry, and just as an example, when the death of Michael Jackson, I think that 22% of the tweets and 20% of the Wikipedia traffic were about one single thing, which of course put a very large strain on all services, and Google thought that we're under attack. You have the Obama inauguration day was 5-time increase in tweets. And of course, if you build your Twitter was building on physical servers, that would be very hard to manage such a rapid increase in tweets unless they had 80% spare capacity always, which would be very, very expensive for them. So then cloud computing enters the pictures. And there is an organization called NIST, which stands for National Institute for Standards and Technology. It's an American institute. I don't know if you've heard of it. I don't know if that is a thing that is big in radio. They do define.
They do a lot of things, and I mean, I often run into them when I'm doing radio channel models and so on. And I'm not. This is something that I should know on top of my head, but I believe that a lot of these images that we're using for training is also based on NIST.
Oh yes, they have this. There's a NIST character image recognition.
Numbers for recognition.
Yeah, that's right. Yes, this is a machine learning crowd. Good. So, but they have this tried to define cloud computing, and they used five words or five properties, I would say. And the first property is on-demand self-service, which says that a consumer can unilaterally provision computing capabilities, such as server time and network storage, as they see fit, needed without any human interaction. So meaning that you can go to one of those cloud providers and you just sign up. Typically, you have to hand in your credit card, but besides that, you're on your own. There is no human, there is no sort of agreement on anything else than it's a standard form, and it's done by yourself. And once you have signed up, you can allocate and configure resources as you see fit. And that's a big difference, because before cloud computing, if you would like to place your servers in a server farm somewhere, that would actually typically include writing a document or an agreement saying this is the uptime, this is the availability to the servers, etc., etc. But the big change here is it's on demand, it's self-service, and it's you who do it when you want to have it. So it's open 24/7. The next thing is called broad network access, and it simply states that the services should be available over a network that access to standard mechanisms, and translated into normal speak, you should use standard networks, and it should be publicly available. And standard networks is TCP/IP, standard protocols, HTTP services, etc., REST APIs, and so on. I think that is resource pooling. I mean, I said at some point that cloud, that Stallman said it was just a business thing, and I think resource pooling is what makes it a business thing, because we're selling compute power for less money than it costs to buy them. So we're selling virtual resources that cost less than physical resources. And how can you do that? Well, the reason is that you sell the same CPU cycles many times by placing several virtual machines or several execution environments on top of the same hardware. So we will pool resources between tenants in the cloud. And of course, that has the benefit is that it will lower the price. The downside is that you don't have full control, and you really don't know who your neighbors are and exactly which performance you will get. Rapid elasticity is kind of tied back into the on-demand part. It means that you can yourself scale up, and you can demand more resources or demand less resources very, very quickly. So you don't have to place an order with the IT department saying, I would like to have a virtual machine, and can you please have it ready by Monday? Instead, you will just have a program that starts a virtual machine when you need it in order to match the capacity that you need right now. And you will see this in the lab today, how you will start it manually on demand, and then you will also see how you can do this programmatically. Okay, and then measure service. Again, it's like electricity bill. You will pay for the amount you use. Simple as that. So the more you use, the more you pay. And if you look on here's it is a couple of years old screenshot from Amazon, but basically you will have, this is a list of the virtual machines. So the virtual machines are called, here's T2 micro, T2 small, etc. That is a class of virtual machine. And then you will get the memory, and then you get some storage that is associated, and then you get a bill. So it costs, in this, was 1.3 cent per hour for the smallest one. And then to the right, here's where we would like to end up. We would like to match our capacity in the red dotted line or dashed line to be slightly above the demand, meaning that we will meet we'll be able to serve all the requests within a given time limit. And when you have this scalability, then having 1,000 machines for 1 hour will be the same cost typically for having one machine for 1,000 hours. That is not completely true, because there are some it's grown to be some long-term contracts, but for if you go for this price tab, you see here, it's the way it works. So here are 10 things that was listed in the paper that we got this morning. So there's some, the discussion early on was about availability, if it's improved or not improved when moving to the cloud. I think that the worries in the beginning was that availability would be a challenge for the cloud providers. But we've seen over the years that the people at Amazon, Azure, and Google provides possibly the best availability you can have. By running things centralized, you get all the benefits of large scale, and you get the best people to run it. So availability is typically very, very high, even if it doesn't say so in the contracts. Typically, they only have 2 nines in the contract you sign when you log in on your on-demand, but in reality, it's much better than that. A problem here is data lock-in. When you do cloud services, one thing that becomes apparent is that once you have uploaded your data to the cloud, it will stay in the cloud because it's very expensive to move data. So it tends to be that you have to select your cloud with some care, because moving computations around is easy, but once you have a bunch of petabytes of data, you will see that will take a couple of months or weeks to just transfer it from one cloud to another. And that goes into the data transfer bottlenecks at item 4. Performance unpredictability comes from the fact that you do resource pooling, so you really don't know what kind of, if you start 2 VMs and you benchmark them on Amazon, you will see that they will actually have different performance depending on actual physical underlying server, who else is being co-located to that particular physical server, and so on. Scalable storage is something that is very hard to do yourself, and something that is, well, I would just say it's a benefit from running in the cloud. Bugs in large-scale distributed systems. I think that one thing we could reflect on with cloud computing is that it's an added layer of complexity. but we are providing a virtual data center on top of physical data center, and we have several virtual data centers on top of one physical data center. So the complexity on debugging your cloud applications is something that is completely different from debugging your local applications. And today I would say that the tools at hand that you will experience is well, not on par what you would expect. So that it's scaling quickly. We mentioned reputation fade sharing. That was the problem early on. I think it's getting better, but the point here is that if you're sharing the same IP numbers, Amazon is providing a bunch of IP numbers to you guys, and the IP numbers that the user of your IP number, the previous user of your IP number might be a kind of a shady business, or somebody in the IP range that you think you're belonging to might actually be a botnet or a service that you don't want to be associated with. So how can you distinguish yourself from the other users of the same cloud service? And then the last thing is software licensing. That is something to consider when you do cloud. If you're going to do scale up quickly and so on, and scale down, I think it's important to note that if you have Windows servers scaling up and down, then you will need licenses for those Windows servers scaling up and down, which is complicated. So everybody who runs cloud basically runs in Linux. So that was a few comments on it. Did I miss something? You guys, you had this as homework. Did I miss something, or can you help me out here? Did I? Nobody read the homework. Now it's time to show.
Maybe my fault, but the file has been sent out.
Yeah. Oh. But if I miss something, let me know. But let's start from the hardware. So here's where the data center can look like. To the lower left, we have the Ericsson data center. We have one of those. It's located outside Kista. On the top right, we have the Facebook data center in Luleå, which is fairly substantial. I think they consume something over 0.5% of the total power capacity of Sweden. So it's a big deal. Inside those data centers, it's actually a kind of big machinery that goes on. So you have and the red thing here in the middle is the servers, and I guess you can that's nothing. And the servers are organized in racks. The power is distributed through power distribution units that powers each rack. And typically you have redundant power lines to make sure that you can deliver even if one of the two power lines, because one might always break. You have computer air handling to cool this and running 1,000 servers, and each server is running at 300 watt. There's substantial heat dissipation in this. So you need to have a very efficient cooling system. And in the case of power outage, and of course you always have power outage, you need to have a set of batteries, a UPS, uninterruptible power supply modules. But of course, those UPS cannot run forever. And first, you need to have one UPS per power line. So there is a application on the UPS system. And then you need to have emergency diesel generators that can power the UPS. And of course, the emergency diesel generator also has to be redundant. So everything here is built to at least sustain a wide number of faults, but without causing a failure. And if you're interested in learning more of data centers work, there's this very nice book called The Data Center as a Computer by Barroso. It's on Google. And I think it's free. It downloads PDF, and it's nice description of sort of the thinking of this data center as one big computer. And inside the data center, we have a set of elements, which is we start with a rack with a server, and the servers are mounted in racks, and typically it's 64 of them. And then we will pair those racks with 64 servers into clusters, and then all those clusters is connected to a cluster switch, and then you have several of those clusters. So if you think of this as a hierarchical network. So for example, then when you write your application, there is concerns if the servers that you're running, if the virtual servers are running on the same physical server, or if the virtual machines are located on physical nodes that are in the same rack, because then communication will be faster, or if the server, your computations are on servers in different racks, so then they have to communicate over the cluster switch, and that will of course affect your performance. On the other hand, it might improve your availability, because if the server goes down, then there will be, if the computations are on the same server or different servers, then if one server goes down, the service can continue. But if the rack goes down, or if the cluster goes down, and so on and so on. So when you design your application, you typically would like to spread out your computations if you are after availability, or locate your computations close if you are after performance. And with that, I will conclude. I think I can take some questions from the audience as so far, because I think I spent my 45 first minutes, and I would like to not wear everybody out completely. So I think that 45 minutes is a good place to take a break. So do you agree that, Hugo, we have a 50-minute break and then we continue?
Yes, absolutely.
Okay, good. So I will be back in 50 minutes. Until then, have a bio break, have a cup of coffee, and make sure you come back with lots of questions, because I have been not so many questions this time. I'll try to be more interesting next hour. Okay, thanks. So is anybody online? Can anybody say something?
Yeah.
Cool.
Here.
So if there is actually a construction ongoing outside my window here. So if you think it's an earthquake on my end, it is. So they're constructing a bicycle road, and you have those big machines, what are they called? Tumblers, kind of, that goes outside here. So everything is shaking. So if it sounds noisy, let me know, and I will try to, speak louder or repeat. Okay. I think it's 10 o'clock again, and I think we should run. I don't know if Hugo is back, but he's not the one who's going to do the homework. He's already done the homework. So I was. So yeah, I was going over sort of the inside of the cloud, the data center. Now we're going to go to the cloud. It is as such. And again, NIST, they define, I had 5 things that was on demand. There was resource pooling, rapid elasticity, metered service, broad network access. Those was the 5 things that made up the properties of a cloud. But in addition to those properties, they also have 3 kinds of services. And one is called infrastructure as a service. Next one is platform as a service. And the third is called software as a service. So I will go back and go over them. So infrastructure as a service, that was the initial one. And that was the one was launched by Amazon, basically saying that you can build your own virtual data center. So they provide a platform where you do virtual machines that you connect over a virtual network, over virtual routers, with virtual storage. and then you stitch things together. So what the cloud provider gives you is the white things in this stack. They will do the physical network, the physical storage, the physical servers, and then they have a virtualization layer. And then they provide you with an operating system that you boot up. And from that on, you're on your own. So if, for example, the servers crash, bad for you. If you hadn't made any backup, well, the bits are gone. There's somebody with the mic on, so maybe we all mute. Unless you say something, because then you should not unmute. Then you should unmute. Okay, and please do. So this is the first layer of cloud, and the user's responsibility for making the application run correctly and make it safe, handling crashes, scaling, authentication, redundancy. And this comes in many flavors. You have Amazon Web Service, AWS. You have Google Cloud. You have nowadays you have Azure from Microsoft, and they have Rackspace also, which is so that is sort of the first version of cloud. And that was the Amazon way, but Google took a slightly different stand in the beginning, because they said, you know, this is very complicated, that people should be able to run up their virtual machines and connect them together, because then they need to know Linux and networking and routers and all this crap. So they instead provided a runtime, saying, you know, what if we instead give the users a Python VM or a JavaScript VM or a Java VM or something similar, and then we just manage that for them, and then we have all those libraries in Java or Python that handles redundancy and storage and communication. And wouldn't that simplify for users? So in the beginning, there was a kind of a race between the infrastructure as a service and platform as a service. But in platform as a service, the user do not manage or control the application infrastructure. You just manage what's inside your Java or Python VM. Typically, you will do subclassing from a Java class or similarly in Python, and you just paste in your code whenever there is a typical call from a user that they should respond to or something. And of course, this is much simpler because it's the cloud provider that handles many of the complex things. And we will look at something called Google App Engine. So, and it looks a bit like this here. So you know, showing code in this. So I'll give you a few seconds to refocus here. But on the top here, you are. So the idea is that Google gives you a virtual machine, and it will start a Java class for you, and you have to just extend that Java class which they run for you, which is called HTTP servlet, and you're going to say, when you do a get request from HTTP, what are you going to respond to that? So it's very easy. So in this case here, that if somebody makes a response, a request for this server, you will simply reply with hello plus the current username. So this is a very simple way to get something running. So this is making it simpler for users to write applications. And if you're a Python head, the same code is shown in the, or almost the same code is shown in the lower part, where you basically just paste in that in response to a request over HTTP, you will just say hello world, and that's fine. So you know, instead of starting booting a Linux virtual machine and figuring out, you know, installing an Apache web server and then writing the Java code to work in that, you will simply just do this. And of course, the downside is that you're limited in what you can do. But if you look on this on a higher perspective, it looks a little like this. You have an application that consists of a front end, and then there is application logic, and then there's a data store in the back, and then to the lower right there is some libraries that the user can use. And all this, the scaling is shown here, that there is 3 front end and 3 app servers and so on. And this scaling is then taken care of by the system. The Google App Engine is doing that for you. So you simply put together a front end, an application logic, and then the data store, which is a function that is provided by Google. So if in the infrastructure service, if you would like to have data that survived the server crash, then you had to replicate it yourself. But here, the data store is actually taken care of by Google. So they make sure that your data is not lost. All the cat pictures are gone, or are not gone. They will be stored forever. So that is a simpler way of writing cloud applications. Unfortunately, this is not the dominant way. I think the dominant way of writing applications is still much more close to infrastructure as a service. But I would vote for this any day of the week. So, but the third category from NIST, the first was infrastructure as a service, the platform as a service, and the third category was software as a service. And here, the cloud provider will run the entire application for you. And this is Google Apps, for example. Then everything that it has to do with application is provided by the cloud provider, and they take care of user authentication, data storage, debugging of the application. There's no installation, there's no maintenance. You don't need a IT guy in the house because everything is done somewhere else. And of course, there's some downside to this, because when this breaks, for example, the connectivity to the data center, or it's very difficult for any business that uses this to continue working. But I think that, and then at Ericsson we are using Office 360. Well, I guess you do us since you're running Teams and the way we work today. So I mean, Teams is typically a software as a service. We have a communication. It's not installed in our servers. It's running somewhere else. We're having this. All the files are stored in the Teams site and so on. And of course, it's very convenient when it works. And if you just try to break down why you would do this, is that if you compare it to traditional software, it's subscription based. It's typically that is the as a service part. You don't have to have it installed in your local machine. It's on the internet. Upgrades, you don't have to upgrade because that is happening in the background. Much of the upgrades is on the servers rather than on the local machines. So it's managed for you. There can be some worries about subscription rates once you are when you're hooked up to this and been using it for a while. Particularly when it comes to data, again, as I said, in the 10 items from the paper, where the data locking was a main concern. And of course, if you stored your whole company's worth of Word files and maybe more machine learning data and a software as a service, and it will take you a half a year to get it out, that is prohibiting for you to select another provider of this service. So, any questions on this as a service? Platform, infrastructure, software. It's clear. Good.
Yeah, it's clear. Thanks.
Cool. Thanks. So the first application, the generation of cloud applications, we then, when I say cloud infrastructure as cloud service applications, were typically you took your application that you had running and you put it in the virtual machine. That would be a database, a mail server, and you try to replicate the physical computer environment that you had in your lab. So typically, with the first generation, you typically have the same names of your server. It's a mail server, and this is the database server, and this is this, and so on. And even if that was maybe not using all the potential of the cloud, it still had lots of advantages over physical running it, because you could upgrade your machines, the physical hosts, without having any downtime. For example, if you're running your Outlook Exchange server on a physical machine or virtual machine, it's a big difference, because if it's running in a virtual machine, then you can just move that virtual machine live while it's running from one physical host to another physical host without the user noticing that it's actually changed location. And then you can put in more memory in the old one, or you can discard the old one and can keep it running on a better machine. You can have two virtual machines providing the same service. So your Outlook or your Exchange server is running on two physical machines. And if for some reason the physical node is breaking on the first one, it would simply switch over. And another thing that is very nice with running in a virtual environment is that it's actually easier to monitor, because you can monitor the virtual machines and probe that and understand issues much better than you can do with if you're running on a physical machine. So, but what happened over the years is that the applications that I just mentioned here, they were just sort of, we say that we forklift them into the cloud. We just took them as is and we put them in the cloud, and then we allocated a virtual machine, and then we ran. And that was some good things about that. But then over the years, what has come up is something called a cloud native. And that is when an application is designed primarily to run in the cloud. So on the left-hand side, you see this monolithic application. You have function A might be the front end of the web server, and function B might be a database, or function C might be something else, and so on. And that's your application. And the first iteration, you will just move that into a virtual machine and then run it. However, they would sort of assume that the functions A, B, C, and D were scaling in the same way. And it might be that if the more workload you get, then you would need 10 times more of function B, but only twice the amount of function D. And that makes it very difficult for those applications to scale. And also, if you do functions A, B, and C, and D, they are possibly have a different upgrade and life cycle rules. So what we've seen over the years now is something called microservices. So we break down all different pieces of our big monolithic services into smaller services that we refer to microservices. And those are isolated services which then can scale independently of each other, which means that they can reside on different physical servers. They can actually reside on maybe different physical data centers. And the fine part here is they are loosely coupled, because there's typically they don't know each other physically. So you have some routing mechanisms that route the calls from microservice A to microservice B, and so on. And you design each of those microservices to be reliable in their own right. And the tools that have been very, very instrumental in this transformation from cloud monolithic applications to cloud native is Docker and Kubernetes. And Docker is, you can think of it as a lightweight. I think you have come across it for this lab, but if you haven't used it before, it's basically, you can think of it as a virtual machine that is more lightweight. So instead of having a full virtual machine, you only have something that looks from the inside as a virtual machine, but it's actually just a Linux process that encapsulates most of the functionality of a virtual machine. And then you have a system called Kubernetes, which is then designed to run those Docker containers and scale them up and down. So each of those microservices then consisting of typically a set of Docker containers that we can add and scale up and scale down. And the benefit of having a Docker compared to a virtual machine is the time it takes to scale up and scale down. You will see that today when you start a virtual machine, that it will take 1 or 2 minutes to start a virtual machine, and then you're going to upgrade it, and then you're going to configure it. So sometimes it takes 5 minutes before a virtual machine is being responsive and can start to be part of the application. And that will limit your ability to scale up and match workloads. So this is the way things are going. Any questions on what cloud native means? Sorry for the noise. It's as I said previously, there are building a bike road just outside my window, so not much I can do about that. Let me know if it's getting intolerable. So, how does this cloud native start? We said that all this infrastructure as a service came from AWS many years ago, and when they started to develop their applications, they it is very noisy. One thing that happened was that all those different services that I had on Amazon Web Services became entangled with each other. So they had this mandate from just Bezos. I think it's kind of funny. It's just a note, but he wrote, he wanted to make the teams work more independently of each other. So all teams will henceforth expose their data and functionality through service interfaces. So instead of having any direct connections or knowing sharing a database or something like that, they should have service interfaces. Teams must communicate with each other through these interfaces. There will be no other form of inter-process communication allowed, no direct linking, no direct reads of another team's data store, no shared memory model, no backdoors whatsoever. The only communication allowed is via service interface calls over the network. It doesn't matter what technology they use. HTTP, core, PubSub, custom protocols, it doesn't matter. Basis doesn't care. All service interfaces without exceptions must be designed from the ground up to be externalizable. That is to say, the team must plan and design to be able to expose the interface to developers in the outside world, no exceptions. Anyone who doesn't do this will be fired. Thank you, have a nice day. And I think that sometimes people say that the last line is a joke and everything else is not a joke. But I think there's some interesting parts here that is sort of have colored the way we do cloud applications today. But if we go back to this picture here, in the monolithic part, you typically were running on the same version of the operating system, on the functions A, B, and C. We're using maybe the same technology, Java or JavaScript or Python and so on, or C, whatever. But in the microservices, that the functions A, B, and C, and D might run on different versions of the operating systems because they are running in their own environment. And they might be implemented in the tool of choice, Python, Rust, Java, which means that the way we work with this is very, very different when we do cloud native compared to a monolithic application development. So it's not only sort of the architecture as such, but also the way of working. So this cloud native allows us to have different tools for different purposes. This is maybe a mixed blessing because it does increase the complexity and it doesn't make debugging any easier, but that's how we do things today. I won't run into this definition. There's something called CNCF, Cloud Native Compute Foundation. They are collecting frameworks and tools that are sort of cloud native branded, and this is one of the charts, and they typically have lots of those. Have, for example, a set of databases, messaging tools, RPC, remote procedure call tools, and so on. So it's a very, very active community. So if you're remembering anything from this presentation, I think cloud native. If you want to look at this, CNCF is a nice place to get tutorials, to get information of the tools you're going to stitch together, and the way they're going to stitch together. Those are going to be microservices that you then put together in a graph that I showed you in the previous slide. So I think microservices is that's the way to go, and the idea is microservices are clean and simple, at least in theory. When you are in reality, it might look like this. Those are microservice call graphs from I don't remember what Hale was. I got this from Adrian Cockcroft, who was one of the architects at Netflix. But in the middle is sort of the 500 microservices at Netflix and their how they interact with each other. And again, each of the services is maybe easy to design and understand, but how they interact is might be troublesome. So the dependence can be that one of the services is slow or is not working, and then that will affect the others in a very hard to debug way. So the way we do things in order to address this, I said, microservices and cloud native was a way of working, is that you introduce chaos engineering. So if you know that your stuff is going to break, so why don't you start breaking it yourself? So this is actually a tool from Netflix that runs on Amazon that is called Chaos Monkey, and this is the term Chaos Monkeys has become a moniker for similar tools like this. And the idea here with Chaos Monkey is that you yourself will kill parts of your services regularly to make sure that every design of the system will sustain a number of faults without failuring. Okay, so in this here, the Case Monkey, you say that could you please have a termination frequency, mean time between terminations is 2 days, and then you say that maybe we should avoid to do this when there's Super Bowl or during the weekend when nobody is here, and so on, and which region should you kill at the same time, and Amazon is built up with, I think it's 18 or 20 regions, and each of the regions consists of 2 to 5 data centers and so on. So when you are killing, like in this case, you're killing maybe all the virtual machines in one data center at once, and then you see what happens. Can the other data centers, the Netflix services runs in other data centers, take over the functionality seamlessly, and so on. And then that's a way of testing. And Google does the same thing internally. They turn off some of their more crucial services on a monthly or bi-weekly basis, just to make sure that nothing is really depending on one single service to be up and running. And that is a way for everybody to make sure that we get high availability. And we do the same, although we don't need a Chaos Monkey, we break things ourselves. This is from one of the failures we had by mistake. Accidentally, very early on, we erased, we installed a new feature. We're actually racking up a new physical server, and then our orchestration system, or installation system failed, and thought we were reinstalling the whole cloud from scratch. And it started by reformatting all the hard drives. So we had to call out to all the customers saying that not only are your services not running anymore, all your data is gone. There's no way to find it. And of course, this was nothing to celebrate, but we tried to learn the lesson, and we had a cake. When I picked up at the bakery, it was actually spelled with a J. So I think I wish I had kept that cake. Could have made another level. But yes, learn from mistake. That's a good thing to remember. And next time, do something differently. So if you then look on Amazon, we have started saying that it was compute and storage and networking. But if you look on the menu of Amazon today, you will see they have compute, and compute comes in many flavors. It used to be just CPU, but today you got a plethora of different CPUs. You get Intel, you get ARM. Amazon is actually doing their own ARM processor these days. But you also get FPGAs and different kinds of large-scale multi-core systems. Storage comes in spinning disks, NVMe, SSD, so you can pick your storage depending on your application. If you want lots for low price, or if you want very high performance. And you have databases, you have all kinds of ML and services and so on. And there are some very nice AI products. So this is kind of a mix of the infrastructure as a service and platform as a service today. And if you look on the where are the cloud players, you see that Amazon is this is the Gartner chart. You go up to the top right, you have Amazon Web Services, followed by Microsoft and Google, and everybody is pretty much left in the dust. And of course, you have Alibaba Cloud, which are large, but not as big as the three main ones. And I think this is the next slide here is it's just maybe mildly interesting, but I think that in 2015 Amazon was adding enough server capacity every day to support Amazon in 2005. So basically the amount of capacity they had before going cloud, selling cloud capacity, they are adding every day to their data centers. So which is, it's for the first year, if you go for the top right picture here, you see that the net profit were flat, but the revenues were going up. So basically they invested for the first 10 years, they invested everything they got into more hardware and just growing the business. So it's a substantial amount of money that is went into building Amazon. And if you look at it today, it's pretty much everywhere, 18 regions, and each region consists of a set of availability zones. An availability zone in turn consists of one or more data centers, and each data center consists of 50 to 80,000 servers. So you get the picture. This is huge. And here comes the thing when you design your application on Amazon, you have to take into account which data center, which availability zone, and which region you want to place your application in order to reduce latency, but also get performance right, because you would like to be close to your customers. And when you run on AWS, you can. We're back here again to the price list for compute VMs, and you can run your compute nodes. You can come in flavors such as on-demand instances. That's the one you go up there and you just ask for. But then you can also have reserved instances, a long-term lower price. I would like to rent a VM for 5 years or 2 years, and then the price goes down. And then you can have spot instances, saying that you bid on the VM, saying I would like to pay 2 cents an hour for this VM, and then you can bid on that, and then they will, if they have some spare capacity and they're willing to go that low, they will sell it for you for an hour, and then you will get a notification 5 minutes before they bring it back. And that's typically, if you're both on Amazon and Azure, they can kill the virtual machine for you for different reasons, maybe maintenance, software upgrades, etc. I think the deal is that you get some sort of notification. It's not always that the notification comes before the event, but there will be a notification, I believe. And the SLA here, they are saying the monthly uptime percentage of at least 99.95. And if you compare that to the radio requirements that we have, I think it's 4 or 5 nines. You have to help me. Is it 5 nines that we run typically?
Yes. That is.
So this is substantially lower. But so if you would like to run a 5 9 service on top of this, then you have to use those different availability zones, etc., to build a service that is more reliable than a single piece of the service. And Amazon also have a functionality for you to do the scaling for you, because as I said in the beginning, cloud computing is by matching the capacity to the demand. So how do you do that? And in Amazon, there is something called CloudWatch. So basically, you can define a bunch of metrics, and that metric could be like in the right figure here. You have a threshold value of utilization. So yeah, if the utilization of a single server or your cluster is above a certain level, then you will add more compute capacity or storage capacity. If it's below, you will decrease the storage capacity or compute capacity. And the same you can do with latency. You can monitor the latency of your requests, and if the latency is too long, then you can take measures to do that. For example, maybe move your computations closer to data, or try to identify the bottleneck and then scale that bottleneck up and down. They have a fairly elaborate way of defining metrics, having alarms, taking actions on those alarms, and those actions can then be sending some notifications to a user or to just do auto-scaling itself. And that's standard by all clouds. You have that in Kubernetes and OpenStack and so on. Okay, so here's a high-level picture of AWS. Start with router, or with the Route 53 with the DNS servers, which points you to. So when you write an application in Amazon, you start by register to DNS, and that DNS will then point users to the right data center. And then you go in and you have some load balancing that will balance your requests to different web servers. Those web servers can do auto-scaling thanks to CloudWatch. And then those web servers typically will require some application logic. And again, they go through a load balancer to the application logic. And the application logic will scale up and down. Typically, you will have very little state in the web services and the application servers. So meaning that you can scale up and scale down without losing data, because all the data is then stored, all important data is stored in a database at the end. And it's on Amazon to make sure that that data will survive an earthquake or a fire or your mistakes. So that brings us to something we called, we discussed this previously, you know, that it's a business model, but it's in many ways a new way of operating and designing services. And something that's been in the business for long is this saying that it's pets versus cattle. In the old world, we had in our lab we have a server called Bob the mail server, Spare the file server. You know, you have your database physically, but and then in the first generation of cloud services, we took those machines and we put them in the cloud in a virtual machine, and then they had the same name, and we upgraded them manually. But what we're learning now is that doesn't run well if you're going to scale up and down rapidly. So instead, we started treating our servers as cattle. So I hope there's no vegans here, but so just take this analogy with some grain of salt. But you know, you will kill the servers you don't need, and you will start new ones as soon as you need them. And then the name of the service will be cluster server 1.1 or 1.2. And we call this infrastructure as code. So one thing that has been very important is the fact that you can treat software in the way, that you can treat hardware and compute resources in the same way as you typically previously used software. You can add new resources programmatically, and you can reduce them programmatically. So you can actually make a program that starts servers and kills servers and connect things together. And that is what you're going to do today. So infrastructure as code it is. And you're going to do this on a system called OpenStack. So when AWS was gaining attention around 2006, and then people were looking at it and saying, can we do something similar in open source? Because the tools, many of the tools are there, virtualization technology from KVM, have Linux, etc. So NASA and a company called Rackspace put together an open source cloud platform that is called OpenStack. And we are running 2 OpenStack deployments on the Ericsson Research Data Center. It's completely free. And what you see on this picture here is just a snapshot from the networking. So we will go through this part. So everybody, all of you who now have an account on Success should be able to log in, and then you'll see something like this. And the name of this dashboard that you will look into is called Horizon. So you will see maybe it would look exactly like this because we have upgraded since I took this snapshot. But you'll see first the number of instances here. So you get a quota of 50, or I have a quota of 50, and I've used 14. The virtual CPUs. And depending on the flavor of my virtual machine, I can have virtual machines that have 1 to 8 cores or virtual CPUs. Then I may consume more virtual CPUs than I do instances. I get RAM, I get 50 gigabyte of RAM, and I get floating IP. And floating IP is a very special thing because when you do cloud, you will allocate your virtual machines on the local network, and that local network is not visible to the outside world. So then you have something called floating IPs, which is an IP number that is visible to the outside world. And then you can take this floating IP and you can stitch it on to one of the virtual machines. And then that virtual machine becomes visible to the outside world. So this is a bit, so remember, you're going to run into floating IPs today. So take a mental note. Floating IP is the IP number that is visible from the outside, and you can pin it on to any virtual machine. Okay. Then you have volumes, which is virtual storage. It looks like a disk drive, and you will use it as a disk drive, but it's simply just a file somewhere in the cloud. So the components here in the OpenStack is you have the dashboard, and then you have something called compute, which handles your virtual machines. You have block storage, which handles your virtual disks. You have something called object store, which is a key value store. And a key value store is simply something you have a name and there's object attached, and that object is binary. So basically you can store any blob at basically any size that the system permits, big or large. And then you have something called image store, which is the image you boot from. Okay, and we will go through all those things in detail. Per will walk you through the different steps on allocating a machine, selecting the image from glance, allocating a container in the object store. We will maybe not look into the block storage, but you will see it as a volume in your dashboard. And all this is done then by authentication using Keystone, and that's what you use when you log in for the first time. And I think that we are now at the point where you are very tired, and I said many things, and we are getting close to where it's really becoming interesting. I will skip a bunch of slides here because I think let's see here. I just want to say that in this OpenStack.
There was a question a few slides back, I guess.
Oh, yeah.
Relates to the file system, and the question is it the same as NAT? It's
NAS, you
out of
mean?
context, so NAT for
Was
about the
that
floating IPs.
Oh no, it's not the same as NAT. You can. It's basically because NAT is basically that you're doing a translation between IP and internal IP. No, it's not. You know, the short answer it's not. It's magic. It might be implemented in a NAT-like fashion underneath the hood, but from your user perspective, you will just have two IP numbers on your virtual machine. So you have two network interfaces. So if you do look on your network on your Linux box, you will see two interfaces, and one is on the local network and one is external network. So think of it as two virtual network cards. That's sort of the logical setup. You have any other questions on this?
Yes, I have a question regarding these microservices.
Yes.
And okay, this is a very nice concept, of course, especially if you intend to open source. And what is the status and the view of Ericsson regarding microservices in mobile networks? I would say that it's like the network operator has an API interface to, for example, change handover algorithms or check what's happening inside the Ericsson infrastructure.
Yeah, I think I will say a few words on that tomorrow, but our core network, that is from the antenna or from the base station to the internet, everything in that part is actually built using as a microservice architecture, and that allows us to scale. So we break down the functionality of the core network into microservices, and that allows us to scale individual parts of the network independent of other parts. And it also allows us to have life cycle management, that is not the whole network has to go with the same pace. You can release different components with different speed. And we typically do continuous integration and continuous deployment for this. So everything the way of working is you make a change, you do local testing, you deploy it to the Git repository, and then you do integration tests with all the other microservices. Once that is passed, it would then move on to a deployment state where you can potentially deploy it directly if you had access, if you wanted to do so. But we can deploy it automatically in our test environments. So I think that we have embraced internally microservices to 100%.
Sure, thanks.
And it's a key tool for us. So yes, so automate everything. So the first thing you will do, sometimes here we should switch, I think. Should I say just a few words on Terraform, or should we leave that for later?
No, I think you could say, give it an introduction to Terraform now. That would be good repetition.
Yeah. So what we will do here in the first round, let's just go to we'll show. So we go to site access here. Let's do some live. I think it's time for some live event. So the first run you're gonna, and Per will run through this again, but here you see it though. This is my one of my accounts, and I can go to compute here, or I go to. So this is one way that I can interact with my code, and then I can launch instances, and you will see me I just give it a name, arbitrary, and description I don't need. Then I can say I would like to have a bunch of those. And I said source, which basically is, sorry, something is very slow here. So you basically, I can where do we want this to boot from? And I say I'm gonna boot it from an image that is something that is pre-cooked. So I take a Ubuntu image, and then I take the flavor, which kind of virtual machine would I like? I will have a C2M2, which means 2 cores, 2 GB of RAM, like this. And then I have the network that I'm gonna attach it to. How about internet? That's nice. You shouldn't do that, by the way. You should use your local network, but anyway. And then I can go on, and then I need to have a key pair. Say that when I log on to the machine, I need to have an SSH key installed in the virtual machine. So when I boot the virtual machine, I tell the system to send in my public key so I can log into it later. So I just choose a key. Pat will go over those. So don't worry if this goes fast. But this is how you do this. And I put the launch, and then my machine will boot. Or in this case, 13 machines or 60 machines will boot. But I don't want to do that. And this is nice and all, but we are all programmers, so this is a bit not how you really would like to do it. So at the first step, you can interact with OpenStack using a command line tool. So there is something called OpenStack, a client, and I think it's if you started your Docker container, I think that OpenStack client is there. So once you start your Docker and have your setup, you can actually do OpenStack server list and the network list, and you can get some information about. And that's of course much faster. But that's not the only way you can interact with the system. You can command line, you can create virtual machines. You don't have to go this clicking and then stuff. So that's too tedious. But it's not only Bash you can use for this. There's a Python SDK, so you can write Python code that will, in this case here, it will start find an image called Ubuntu 1804. It will then find a flavor that is the kind of virtual machine. It will look on the network, it's the internet, and then it will create an instance for you, programmatically using Python. And another way to do this is, of course, curl. So everything is just a web request. So there is another way of doing this by doing it in JSON and REST. So there are many ways to interact with this, but we're not going to do that. I'm just going to tell you that it's possible. What we're going to do is some much smarter, and it's called Terraform. And Terraform is a declarative way of specifying your system. So you say, I would like to have a server, I would like to have a network, I would like to have a router, I would like to have a firewall set this way, I would like to connect the routers, and I would like to have those SSH keys installed in my machine, and I would like to have a disk, and I would like to connect this disk, and I would like to mount that disk. So then you can put up a bunch of states that you would like to have the system to have. And then Terraform is so kind to you that it actually will create a plan on how to figure out, if I want to connect servers, I better have the servers first. So then they create the servers. And I cannot install the SSH keys before I have a server, so there has to be an order. Then Terraform is creating that plan for you. And the cool thing is that if you were to change something in your states, it will figure out a plan to go from your current state, which is that you have 2 servers, and you're saying that you would like to have 16 servers. Then they would figure out I need to start up 40 new servers for you. So it would go from, it will know your desired state, your current state, and it will create a plan from going from one state to another. So that would be the second step of your day-to-day. First, you will go through the click and manually doing things, hassle, which we learn, the elements of cloud. Secondly, you will understand the power of automation. And high-level application you're going to make is a visitor counter. And your guys are too young to remember this, but back in the days, that was the coolest thing you can have on your page, saying, you know, how many people have visited my page. So everybody had visitor counters. And you're going to make one today. And it's not going to look like this guy here, because you're going to make a bunch of machines, and when you log into this, each login will actually have it increasing the counter, and not like in this case where everybody's seeing the same number. So when you log in the first time, you're going to see a 1, and the second time you're going to see a 2, and the third time you're going to see a 3. And you're going to log into different machines, showing that, and you're going to scale up and scale down different machines using Terraform. So adding another machine or removing a machine will then allow you to get more front-end servers that you can connect to. And once you connect to each of those servers, you will see that the counter increases. Yes, and I think that's done for the first lecturing part. It's been good 2 hours, and I really thank you for
so
those of you who haven't.
Up, Johan.
Sir?
Someone is raising a hand.
Yes.
Thank you for the lecture. Could you please draw a distinction between Terraform and Helm?
And
Helm. Let me.
Helm is Helm is I don't know if Helm is actually doing a state for you, because that's very much an imperative way of configuring things.
Mm-hmm.
So what we do in Terraform, we set up a number of states. For example, as a set SSH keys, but it's my understanding that the Helm chart is actually setting up a system more like a bash script. It goes from start to end. And if you were to reapply a Helm chart, I don't think it is aware of the previous state.
Mm-hmm.
So you know, so it's like you can run the Helm chart once again, but then if you say you're gonna, if you can't run the Helm chart twice, because it would say those machines already exist. It's
Yeah.
there. So the difference here is the creation of plan and the idea of state being declarative rather than a Helm chart is imperative. While, you know, some of the things are state, like the desired number of servers, for example. I think you could reapply a Helm chart if you only change the servers, but not the full Helm chart.
Mm-hmm.
So you know, it's like running a script twice, but this is not a script. Terraform is as a declaration of state.
Okay. Thank you.
Was that a quick answer, or was it just words?
Actually, I think it would be more clear when we go through it, because right now I've never worked with Terraform, so maybe it's because of that I'm a bit confused between Terraform and actually Helm. But yeah, I think it would be more clear when we go through the assignments.
Good. Well, hopefully so. Any other questions? Thank you so much, guys, and see you in 15 minutes then.